This is chapter 6.3, exercises 37 through 40 and 43 through 44. This section of the book, 6.3, has to do with parametric equations, and especially real-world uses of parametric equations. We're going to be studying windows and making graphs of basic parametric equation situations in this exercise set. And specifically, I'm going to work out the problems, odd number problems, 37, 39, and 43. So this first one, simulated foot race. Ben can sprint at the rate of 24 feet per second. So this would, Jerry sprints at 20 feet per second. Ben gives Jerry a 10-foot head start. Parametric equations can be used to model the race. So basically, this top equation here is going to be 20 feet per second. That's going to be Jerry. And this other one down here is going to be Ben. And we have a conflict of units because the sprinting happens in the units of feet per second, yet we're simulating in part A, finding a viewing window, simulate a 100-yard dash. Graph simultaneously with t starting at t equals 0 and t step equals 0.05. So we have a choice. We can take these feet per second and change them into yards, and 24 feet per second, that's going to be 8 yards per second. But 20 feet per second, to change that into yards, we have to divide that by 3. Not very comfortable. So let's take this 100 yards and convert 100 yards into feet by multiplying by the conversion factor. We have 3 feet per yard, and yard over yard cancel, and so we have 300 feet. So we're asked to place a viewing window. We can just work this out in advance. For the X viewing window, we're going to go 100 yards, which is 300 feet. So we can call that from X min of 0 all the way to X max of 300 feet. And we can, just for extra measure, just go maybe 10 feet beyond. As far as the Y window, if we go from 0, a height of 0, and we have our Y of 3 and a 5, let's go ahead and put, we can just take the standard 6.67 that comes with the TI Inspire standard window. So we'll just leave it like that. And I think with this we have everything we need. Let's go to the calculator. In the calculator we get a new window. I press the graphing icon, go to menu, and go to 3, graph entry edit. And then we have option 4, which is parametric. So we'll just press 4, and we're given x of 2 and t. So let's put in, I think Jerry is 20t. As far as y, let's take a look at that. It's going to be 3. Okay, so that's going to be Jerry. So 3. Now we have time between 0 and 6.28 seconds. Well, no one in the world has run a 100-yard dash in as little time as 6.28 seconds, no human being. So we're going to make that 20 seconds just to be sure. And we recommend a t-step, or at least they do in the problem, of 0.05. And so that's what we're going to put here. I found that you can also use 0.04 sometimes. And so we enter this equation here. We see this red horizontal line. So let's go ahead and try to enter another one. So if we go to tab, we have x of 3. So we're going to put, I think we put, was it 24t minus 10? Let's just be sure here. Yeah, 24t minus 10. So 24t. When you start on this, it's easy to put x instead of t until you get used to it. And we're going to be at a height of 5 feet. And again, we're going to change our time to 20 seconds. And our t-step to 0.05. So here we go. Let's just check that out. So we enter that. We see in the black here. And let's just go ahead and set the window now. If we go to menu, window zoom, that's going to be 4. And we're going to go to window settings. A lot of people like to use just zoom out. Well, again, our X-min was set up as 0. Our X-max was set up as 310, as in 310 feet. And then we were going to leave Y-min we're going to call 0. Y-max we're going to leave at 6.67 feet. So we tab down, we go here, press OK. So we see this. So we have here, it looks like Jerry is down here in the red and Ben here is in the black. It's going faster. Let's make sure we have everything correctly. Yeah, it looks right. Okay, so we've graphed it. We have viewing window. Everything is good so far. Who's ahead after 3 seconds and by how much? Well, we go back to the calculator and we can go to menu, trace, which is option 5, graph trace. It automatically puts us down here on Ben's. I believe that's Ben is the slower runner here. Actually, Jerry's a slower runner. So it puts us in Jerry's, and we're at time 7.79 seconds. So if we go to the left, and I guess we can T-step over this way. It looks like it's going, I have 0.05 is the T-step, but it's, but here we are at T equals 3 seconds. So at T equals 3 seconds, Jerry has covered 60 feet. So at T equals 3 seconds, Jerry has covered 60 feet. And it really makes sense, doesn't it? Because if we have this 20t, it does make sense. Let's try see if we can see what Ben, how far Ben has gone. Well, I'm going to go up here, and we just happen to be at t equals 3.03. Let's see if we can go over to that. If we just arrow once to the left, we have t equals 3 now. Well, Ben has gone 62 feet. So at t equals 3 seconds, Ben has covered 62 feet. So we can conclude Ben is ahead and by how much? By 62 minus 60 feet, or 2 feet. So Ben has made up the head start of 10 feet, plus he's passed Jerry by that time. So this would be our answer to part B. And just a quick glance at 35, this capture the flag problem. One thing I recommend doing is changing this in the second parametric equation, this y sub 2 equal to different than 3, because otherwise it would be harder to see these things together. So here we're given a window, and we can just work this out. Give us a window to work with, gives parametric equations like 38. Okay, next on our problem 39. Famine relief airdrop. A relief agency drops food containers from an airplane on a war-torn famine area. The drop was made from an altitude of 1,000 feet above ground level using the equation to model the height of the containers during free fall as a function of time t. Well, we're going to do just one equation. In this one, what we're going to do is we have a ground level here, and we have a plane flying up here that makes a drop. And the level of this plane up here is 1,000 feet. Okay? And it's going to drop here towards ground level. And to get a parametric equation to work this way, we're going to change the y value. Now, let's just do the window first. The window, what we're going to have be is, I'm going to put over here left, x. We're going to go from x equals 0 to x equals 5. And for the y, or the range that we're going to be able to tell, we drop from 1,000 feet. So I'm going to go ahead and we go down to ground level. So we're going to go ahead from 0 all the way to 1,100 feet. And that 1,100 leaves some margin above that 1,000 level. And the parametric equation, well, when we drop something vertically, the horizontal will not change. So we're going to just say, for this parametric equation, we'll say x of t is equal to 2. And I'm going to explain why I use 2 and not 0. And then y of t, now we're measuring in feet. Now we're going to start at a height of 1,000, and we're going to subtract from it at a rate of 16 t squared. Now, how were you supposed to know this? Well, in our ACP formula chart, we were given vertical position, and that would be y equals 1/2 gt squared. Okay, and then with the starting velocity and so forth. But what happens is g is given here as 32 feet per second squared. So if we take this 32 feet per second squared and plug it into in the place of g, what's negative 1/2 of 32? Well, it's going to be 16. So that's where we get it from. So that's going to be a crucial thing. If you're in feet, it's going to be minus 1/2 or minus 16 t squared. If you're in meters, it'll be minus 4.9 t squared. So that's just something to look out for. So here we are, back at our problem, and that's gonna be it. We have an x of t and a y of t, and we have our window set up here. So let's go ahead and do that. We go ahead and Control I, get a new page, add graph, and we go to 3, and that's going to be graph entry edit, and graph parametric. And for this one, we have x for t equals 2, and y is going to be 1,000 for 1,000 feet minus 16t squared. And then we have for time, it's going to take us a while. That probably will work okay for the drop. That'll probably give us plenty of time. I'll just make it 10 in case. And then t-step, we can use 0.05 like we did for the last problem. I'm going to use 0.4. I don't know if that works any better. And then we press enter, and we get this magenta vertical line in the parametric equation listed here. Next, we'll go to the window, and for our window settings, we want our x-min to be 0 and our x-max to be 5. And then we have our y-minimum, we put as 0, and our y-max we put as 1100. And press enter. So we see this. Okay, so that's really the graph, and that's part A. We can see the magenta graph here starting at 1,000 feet in elevation here and heading down to the ground. Let's look at the problem instructions. Okay, use parametric mode to simulate the drop during the first 6 seconds. Well, I set the time to 10, so that would be fine. So it says simulating. We've done it. Let's just go ahead and use the table. We go to menu, trace, 5, graph trace, and it takes us automatically down to the bottom. If we go up here, the first 6 seconds to get, we have to get to time equals 0, right? Well, if we get to time equals 0, we should get to 1,000 feet. Now notice it took us down, so it's going up very slight, isn't it? I'm just scrolling up like this. There, it's taking us up here. There we are. So at t equals 0.1, it says we're at 1,000 feet. And this one here, 1 times 10 to the, this is that's exactly what it is. So that's 1,000 feet. So we go to the right here, and so here we are at 1 second, almost. There we are, 1 second. We fall into an elevation of 984 feet, and so on, down to 6 seconds. Okay, so we just keep on going down to 6 seconds. We're up to 4 seconds now, 5. Okay, we're getting close to 6. So after 6 seconds, we fall into an elevation of 424 feet, which we've dropped. I think that's going to be, what, 576 feet from where it initially dropped. So there we are. Next, after 4 seconds of free fall, the parachute's open. How many feet above the ground are the food containers when the parachute's open? We go back to the calculator, and we can go back to 4 seconds. Here we were at 6 there. We go up to 4. And we're at an elevation of 744 feet. So our answer is 744 feet, which is a drop of I think 256 feet. Now there's going to be other things to take into consideration, like drag for the parachute, but this kind of eliminates that. Okay, here we have a similar type problem to number 39. Good luck with that. Now we get to 43, hitting a baseball. And Kevin hits the baseball at 3 feet above ground with initial speed, 150 feet per second, an angle of 18 degrees with the horizontal. Will the ball clear a 20-foot wall that is 400 feet away? Well, we're given our equations, our parametric equations right here for x and y. Let's go ahead and do one more thing, and that would be to set a window. So for a window, we're going to have x. We're starting from x equals 0, and we want to clear a wall that is 400 feet away, so we can go beyond that. We can go maybe to 410 feet. And for the y value, that's going to be harder to figure because, well, we know we can start at 0 because that would be ground level, but then we're hitting the ball into the air, and you can use maybe 100 feet. It doesn't have to be exact, and if you're too low, it's always easy to come back and correct. So we'll say 100 feet above ground. So we have the parametric equations, and we have 18 degrees. Now, what I did in an earlier video is I converted the cosine of 18 degrees and sine of 18 degrees so we could keep account of that better, and I'll explain why right here. I'm going to go to Control I, add graph, and then we have parametric menu 3, 4. Okay, the x equation we have is going to be, make sure I get it right here, a 150 cosine 18 degrees t. Okay. Parentheses 150 times cosine. Now, do you notice in this, when we graph, we have our angle in radians automatically, and so if we put just a number in here, in this case 18 degrees, we would have the cosine of 18 radians. But in order to fix that, we can actually put the degree symbol there, which I'm going to do by pressing the little pi symbol right here. And right below the pi is a little degree. And so this tells that even though we're in radians here, we are, because of the symbol, instructing the calculator that no, we really want this in degrees. And then we go outside here and we multiply this by t. I'll put times t. And then for a y, well, we're going to be 3 feet off the ground, plus we're going to have, again, similar to the x, we'll have 150 times, in this case, the sine. I don't know if you remember from trigonometry, we said our cosine is x and our sine is y. And so with elevation is y. And again, we're going to convert this to degrees by putting the degree symbol there. And then we put times t out here. And then we're going to have minus the force of gravity, which position to the force of gravity, 16 t squared. And then for this, we're going to go ahead, and I think we have enough time at 6.28 seconds. I'm going to convert this to 0.04 seconds, and that should be everything. I'm not sure it's in the exactly the same order, but it shouldn't make much difference. Yeah, I kind of reversed the order. I put 3 plus this thing here minus 16t squared, but everything, because of the commutative property of algebra, it's going to be just fine. So if we go here to the calculator, and press enter, we get this green fly of the ball. Now we just have to change the window to what we figured and go to menu, and it's going to be window zoom, window settings, X-min is 0, and we're going all the way to 410 feet X-max. Our Y-min is 0, and our Y-max is 100 feet in elevation. Hope that's enough. I think it is. And we press that. So yeah, that's fine. I mean, it doesn't fit perfectly, but 50 would have worked just fine too. But let's see what we're trying to find. We've graphed it now. Looks good. Approximately how many seconds after the ball is hit does it hit the wall? So we go back to our graph parametric equation, go to menu, graph, and we'll go trace, graph trace. It takes us right to the apex there, and we can just go all the way to 400 feet. And we're over here to 308 feet. Okay, we're close to 400 feet now. Okay, we're at 399 feet. We're at 2.8 seconds. At 405 feet, we're at 2.84 seconds. So it's going to be about 2.8 seconds. It's going to be actually a shade after that. So we'll say about 2.8 seconds. We'll say about 2.8 seconds. Okay, and then next, how high up in the wall does the ball hit? Well, we look at our height at 399 feet away from home plate. We're at Y value of 7.35 at 7.35 feet. So we will say about about 7.35 feet above ground. Okay, and now we come to this last part, writing to explain. Well, writing to explain why Kevin's hit might be caught by an outfielder, and explain why his hit would likely not be caught by an outfielder if the ball had been hit at a 20-degree angle with the horizontal. Well, I would just say at 7.35 feet above ground, an outfielder should be able to reach and catch the ball. To reach and catch the ball. Now, of course, if positioned properly. This ball is getting to the fence in 2.8 seconds. So they explain why his hit would likely not be caught by an outfielder if the ball had been hit at a 20-degree angle with horizontal. So we go back to the equation and do that. If we go to tab, we'll go up to this one here, and here we're going to take this 18 and change it to 20 degrees. We do the same thing in this y part of the equation. And so we've changed everything. I mean, not everything, just the angle of inclination, we call it. If we do that, and here's what we see. Path of the ball. Well, let's go ahead and trace again. 5 trace, graph trace. And here we are at 395 feet. We're at 21.2 feet above the ground. We go over to the right, at 400 feet away, we are 19.7 feet off the ground. So that's going to be almost hit the top of a 20-foot wall, right? The very top of it. Now, it wouldn't quite clear the fence. But we will say for this one, we will say the ball hits the fence uh, 19.7 feet off the ground. Off the ground. And therefore impossible to catch. And we will say at 20 degrees inclination, the ball hits the fence. So anyway, we have all of our answers. I want to just show 44 briefly. In the next video lesson starts with problem 45, and problem 45 refers back to problem 44. So we're going to do 44 as part of 45 in the next video lesson. Anyway, I hope this has been helpful to you. Again, this has been basically about getting around in the calculator. Good luck with the even number problems, and thanks for viewing.